A shear zone is a fundamental structural feature in geology representing a region of the Earth's crust or lithosphere where rocks have undergone intense deformation due to differential stress. Unlike discrete faults, which are often localized fractures, shear zones are broader zones where rocks experience ductile, brittle, or a combination of both types of deformation over variable scales. Shear zones are significant in understanding tectonic processes, metamorphism, mineralization, and the mechanical behavior of the lithosphere. A shear zone can be defined as a planar or curvy planar zone of intense strain characterized by the relative movement of the rocks on either side. The deformation within a shear zone can range from brittle fracturing to ductile flow depending on temperature, pressure, and rock type. Key characteristics include strain localization, foliation development, mineral alignment, and in many cases the presence of mylonites or ultramylonites in high-strain zones. Shear zones can vary in thickness from a few millimeters to several kilometers. Their internal structure often shows gradation from highly deformed core zones to less affected outer zones. These zones are classified based on geometry, kinematics, and deformation mechanisms. Shear zones are broadly classified into ductile, brittle, and brittle ductile types. Ductile shear zones occur deep in the crust, under high temperature and pressure conditions, where rocks deform plastically without fracturing, producing features like mylonites, schistosity, and lineation. Ductile shear zones are important in understanding deep crustal flow and tectonics. Brittle shear zones occur near the Earth's surface, where low temperatures and pressures favor fracturing. These zones are characterized by faults, breccias, and cataclysmites, and they play a crucial role in earthquake mechanics and fluid migration. Brittle ductile shear zones form under intermediate conditions and exhibit a combination of brittle fracturing and ductile flow. These zones often mark transitions between upper and lower crustal behavior. Shear zones display distinctive features such as foliation, which is commonly developed parallel to the shear plane due to mineral realignment, lineations, which indicate the direction of maximum stretching and are often observed along the shear direction, mineral stretching, recrystallization, and grain size reduction also contribute to the characteristic textures of shear zones. SC fabrics are a common diagnostic feature consisting of intersecting planar structures where S surfaces represent foliation and C surfaces correspond to shear planes. These fabrics help geologists determine the sense of shear, whether normal, reverse, or strike slip. Other features include boudinage, asymmetric faults, and tension gauges, which provide insight into the strain intensity and deformation history of the rocks. Understanding the movement within shear zones requires analyzing strain patterns, and kinematics. Geologists use markers such as deformed pebbles, fossils, or mineral grains to quantify strain and determine the sense of shear. Techniques like Frye analysis method, which analyzes the spatial distribution of objects like mineral deposits or rock particles to identify directional trends and strain, and finite strain ellipsoids are applied in the laboratory to measure deformation. The kinematics of shear zones can be simple shear, pure shear, or a combination of both. Simple shear involves displacement parallel to the shear plane, while pure shear involves flattening without rotation. Most natural shear zones exhibit a combination of these motions, which influences rock fabric development and metamorphic reactions. Shear zones form in response to tectonic forces such as compression, extension, or lateral displacement. The formation of shear zones facilitates crustal accommodation during a large-scale deformation and contributes to the development of mountain belts. Geologically, shear zones are significant because they localize strain and serve as conduits for fluid migration, promoting metamorphism, metasomatism, and ore deposition. Many valuable mineral deposits, including gold, copper, and tin, are associated with shear zones due to enhanced permeability and fluid rock interactions. Shear zones have numerous practical applications. In mineral exploration, identifying shear zones is critical because they often host economically significant ore deposits. Mining operations target these zones for gold, silver, and base metals. In civil engineering and geotechnical studies, shear zones influence slope stability, tunnel construction, and dam foundations. Understanding the orientation and mechanical behavior of shear zones ensures safer infrastructure development. In petroleum geology, shear zones can act as both traps and conduits for hydrocarbons. Knowledge of their structural and petrophysical characteristics aids in oil and gas exploration and reservoir management. Modern technologies have transformed the study of shear zones. Remote sensing and satellite imagery allow geologists to map large-scale shear zones in inaccessible terrains. Geographic Information Systems, or GIS for short, facilitate the integration of structural data for spatial analysis and modeling. Seismic tomography and geophysical surveys, including gravity and magnetic methods, help identify deep-seated shear zones and their subsurface geometry. Digital modeling, finite element analysis, and 3D visualization provide insights into stress distribution, strain patterns, and potential zones of rock failure. Electron microscopy and X-ray diffraction enable mineralogical and microstructural analysis at microscopic scales, allowing precise characterization of deformation mechanisms. Additionally, drone-based photogrammetry is increasingly used for mapping and monitoring exposed shear zones in the field. Notable shear zones include the Great Glen Fault in Scotland, the San Andreas Fault system in California, and the North Anatolian Fault in Turkey. In each case, shear zones illustrate a combination of surface and deep crustal deformation influencing tectonics, seismicity, and resource distribution. In West Africa, ancient shear zones like the Iberian and Pan-African shear systems are associated with gold mineralization, emphasizing their economic significance.